All right, so I'll get to the announcements here. So there's only two more lectures, really. So this lecture and the next one is kind of the last unit. And then next week, Thanksgiving week, so there's only a Tuesday lecture scheduled. That's basically a course wrap-up lecture. So it's not a critical lecture. It's sort of just make sure that we cover all the topics we need to cover in VRTs that might bleed over from this week, gives us a little slack there. And then just generally lets us reflect over the course. And then there's Thanksgiving. And then the week after that, which will be the last week of classes, Tuesday will be the final exam review lecture. So bring your questions. And then Thursday will be stage one. So basically that last week will be Tuesday will be the final exam review lecture. Wednesday will be where all your final report stuff and the presentation will be due that night. Thursday will be stage one of the exam. You'll have your peer reviews due Saturday. And then Tuesday, or I'm sorry, not Tuesday, I think it's Thursday. It's on the Canvas site, which day we're scheduled for. I think it's Thursday, but we'll double check on the Canvas site. Will be stage two. So the stage two will be during final exam week, but it's run just like the midterm. So stage one, you can come to class or you can take it at home. Stage two, you can take it home or you can come to class. You'll be given a couple of days of availability for both. But stage one will be timed and stage two will be not. Stage two will be group, stage one will be individual, exactly the same as the midterm. So that's kind of the timeline moving forward. The input modeling reports, I have groups 12, 13, and 14 to finish. I got some emails when I was grading about grades changing and people confused by that. So I had to go through and hide all the grades to prevent some of that confusion, but I will finish those last three groups after this class so that those grades can be released. But I've tried to put very detailed feedback on everyone's the reports to help you sort of guide you. Nobody's in terrible shape. Everybody's got a good system and there's sort of a path forward. So keep going with that. Just try to take my comments into account. I'm probably going to grade all of them. And after I see the distribution of all of them, add a couple of points just because I want the feedback to be more important than the grade. So this will be one of the only assignments that I kind of curve by a couple of points just to make sure that everybody feels like it's a useful and not punitive assignment. All right, so the ICA, there's ICA-L that's out. This is the last normal ICA. Then ICA-M will be that final exam review one. So homework J2 is still out there. It's an arena-based homework. I've gotten a couple of questions over email about it. You pay attention to some of the output data tips just for processing that data. You don't have to use the process analyzer or OptQuest, but it's a good opportunity if you want to experiment with that. Labs, no more lab experiences. So use the lab time to work on your final projects. So try to use that extra time that you're not working on labs to work on that. That said that, lab 10, with the availability window includes this week, right? So lab 10 was due a couple of days ago on Sunday, but I've given you the extra week to do it. So you can, if you want to maximize that extra credit option, because lab 10 is 50 points graded out of 30, then you've had all the last week and you've got this week to do it as well. So, so you've got that time to do lab 10 if you're interested in working on that. Final project, I already talked about the modeling reports. Again, just kind of the big reminders that the Wednesday of the last week of class, that's when your final report and presentations are due. And then once all of those are in, we randomly assign one presentation per person and one final report per person. And the peer reviews of those will be due Saturday of that last week of classes. All right, otherwise, final review stuff. After ICA-L has closed, ICA-M will become available. Actually, it might already be available. You can take it multiple times. You get your highest grade. It's due before the review lecture, which is in the Tuesday of the last week of classes. Lecture M is that Tuesday. There's some practice ICAs already available for the pre-midterm. And then after lecture M, this same ICA will be re-released as a practice version for the post-midterm content. So lots of practice there. You can also find example exams from previous semesters, extra problems, etc. So the same sort of study material we had for the midterm, we've got available for the exam. Plus there's all the midterm material if you'd like that. As I mentioned, same setup as the midterm. And then a detail that may be interesting to you is that because I need stage 1 to fit into a class period, the whole exam is midterm length. So even though final exam periods are 110 minutes, the exam is designed to fit within a 75-minute period. So basically it's designed to be the length of a midterm. So, and that's how we can do the 2 stages. So it's not going to be any longer than the midterm. It'll be a similar number of questions as the midterm, but it will be cumulative. But we'll connect with things like you did a chi-squared test before the midterm. After the midterm, we know how to do chi-squared tests. We just do them on things other than the uniform distribution. So you could imagine seeing midterm-like questions, just maybe with a little more elaboration towards the post-midterm content. All right, so any questions? Covered all this. I think I covered all of the major updates. Also look online to see if there's any questions. Yeah. I think I mean to give you the same number that you had on the midterm. So I'll double check, but I think if you look at the syllabus, I have it in there, and I think it's the same for the midterm. So I'll double check and then add an S if necessary to this slide. But the midterm and yeah, or I'd say the syllabus would be the best source of that answer, and I'll check that and then update that. All right, and then let me, any other questions? Just logging into the question tool. Hope the audio sounds fine online right now. Okay. All right, great. All right, so I hope everybody knows when you're now at the point of doing your final reports, don't you, like if you're ever estimating a parameter, so you're estimating a performance, for example, don't give me point estimates. So we're breaking this point estimator habit. If you run a set of replications on your sim and it comes out and the average waiting time is 3.6 minutes or something like that, don't tell me 3.6, tell me the confidence interval. Well, actually it's from 3 to 4 or something like that, or 3 to 4.1 or whatever. Because again, the 3.6 doesn't really, it's like a 0% confidence interval. If you reran that experiment with a different set of random seeds, then even though it's exact same simulation, you might not get 3.6 anymore. You might get 3.2, you might get 0, you might get 30. So the confidence interval tells us that if I were to run this experiment again, where would likely the next estimates be? So in other words, how confident can I be that it's actually near 3.6? So give me confidence intervals, don't give me points. It'll be tempting to give them points, but confidence intervals are much better. So, and I gave this example before where you can summarize a lot in one confidence interval. So if you ran an experiment and it gave you an output that was had a confidence interval between 0.671 and 0.898, then what that confidence interval tells me is that if you were worried that your wait time was 1 minute, well, you could reject that. The wait time's less than a minute. Great. If your target was 0.75 minutes, then you can say, and by the way, your target seems to be within our confidence interval. I can't guarantee we're not over your target, but I can tell you that our target definitely, or your target is definitely within the confidence interval. If your target was less than 0.9, then I can say with 95% certainty, your the actual performance is less than the target. So stop giving means. If you give a mean, make sure you include plus or minus, and if you can, confidence interval, if you meet the assumptions of that. If you can't, a standard error of the mean is not bad. It at least communicates the variance in your estimator, which is important. So, kind of along that idea, if you're running one sim, so it's totally okay for your final projects to do an optimization problem. And an optimization problem is not really an analysis of one system, but I've mentioned like interventions, like you can model coffee shop as is, and then model coffee shop of the future. And coffee shop of the future might look qualitatively different, but if you actually just look at coffee shop as is and realize there's 3 decision variables there, like number of cashiers, number of baristas, and I don't know what some other third thing. One of those decision variables is probably not worthwhile to talk about in simulation, because with one of those, I know that if you just increase the number of cashiers, it's probably going to be better for the customer. But you would then have to say, but is it worth the cost of the extra cashier? So cost is a big important thing, but I'm not really learning anything by running the simulation. Now, if you have 2 decision variables, like I could add a cashier or I could add a barista, that's something that gets a little, or I could do both, I guess. Of course, doing both is probably going to be better for the customer, but maybe way too costly. So on a budget, I only get one of those. So that's actually not quite at the one system design. That's an example of a 2 system design, but you really only build one sim model for it. And you just adjust the capacity. So my cashier capacity goes up or my barista capacity goes up. And that would be totally fine to just optimize over, that simultaneous optimization space where I have a 2-dimensional thing that I'm trying to optimize. That's totally fine to do for your final project. And just tell me which one's better and which one, and then better, if that's in terms of profit gained per hour, make sure to include the cost. So maybe a barista and a cashier cost the same, but still those costs are going to have to be relative to the do nothing case. When the do nothing case costs me nothing. So even though I know I'm going to get more profit per hour by increasing my throughput, if I subtract off the cost of the extra personnel, I might actually be better off doing nothing, even though I got longer lines. So make sure to include costs. And when you're doing your final projects, even though I'm going to talk about comparing one system to another, by the other system, it really just could be an optimized version of the current system, just so long as you're doing something that gives you a result that is not obvious ahead of time. So I don't know ahead of time whether it'd be better to add a cashier or add a barista. So that's why I need to do the sim. I do know ahead of time adding a cashier is going to probably be better and adding a barista is probably going to be better. That's something I probably don't need a sim for. So hopefully that makes sense. So getting back to the performance estimates, just to summarize everything we've done over the last unit, start out with one system and you can run a bunch of replications of that one system to get a performance estimate, a point estimate, and the variance on that, and a variance estimate, which you can convert into a variance on the estimate. And then from there, we can turn that into a confidence interval. And that confidence interval, that one sample confidence interval, helps us reject any performances outside the confidence interval. Your performance is not that. And it basically says your performance could be anything inside the confidence interval. So even though we define confidence interval, we anchor them by their center, as statisticians, as empiricists, forget about the middle of the confidence interval. It doesn't exist anymore. Stop, just make it kind of like disappear from your vision and only look at the left and the right side of the confidence interval, because that interval is all you care about. So that's what you want to report to people. If somebody says, well, if you need to boil that down to one number, if they force you to only give them one number, then begrudgingly give them the mean. But if they allow you to say 2 numbers, then give them the interval, because that's the honest way of reporting performance. And it summarizes so much. And so, in order to form this confidence interval, assuming these are normally distributed data where each replication was independent, then we know there's r minus 1 degrees of freedom. That's our standard error formula. So we put in that degree of freedom and that standard error into the half-width formula. So the half-width formula right there is just the critical t-value at that degrees of freedom, scaling up times, the standard error of the mean, which is that formula there. All half-width formulas are this. You're just changing the degree of freedom in the critical t-value and the standard error of the mean. All half-width formulas, regardless of what type of half-width it is. That's what you're doing there. So as we experimented with, I think on lab 9, you can, if somebody gives you a 95% confidence interval and for some reason you want to convert it to say a 90% confidence interval, you can just scale it. You don't have to rerun, redo this whole formula up here. You know, that just swaps out the t-value. So we could go and say, well, what's the critical t-value for a 95% confidence interval? It's the thing in the denominator here. What's the critical t-value for the 90% confidence interval, which is the one in the numerator? And then we can scale our existing confidence interval, which is this formula here, to our new confidence interval. And if we're going to a less confident confidence interval, is our confidence interval getting bigger or smaller? How many people say smaller? A hand or two. How many people say bigger? So again, the question is, if we're going from a more confident confidence interval, 95, to a less confident confidence interval, 90, is our confidence interval getting bigger or smaller? So as we decrease confidence, what do we do to the confidence interval? So I'll ask that again. And online, you feel free to put in the chat whether you think it's smaller or bigger. So I'm getting some answers in this chat. So if I decrease confidence, do I make my confidence interval? How many people say smaller? A few more hands. How many people say bigger? I see a hand or so. Well, so how many people would like to, does anybody would like to defend their answer? So is there, yeah, was that a hand? Okay, so, and I saw a hand behind, I'll get to that. So just to repeat for everybody who didn't hear, so that the comment was if, as an example, if you're 100% confident, the claim would be that confidence interval would be large, negative infinity to infinity, because you're 100% confident you're grabbing everything. And if you're 0% confident, it would be a single point, because it's very unlikely the actual value is what you estimated. Was there a question or comment? That's right. So that was a great comment too. The point here is noticing that if you go to a less confident confidence interval, you're increasing your type 1 error, you're increasing your alpha. And so if you're increasing your alpha, that threshold for rejecting things becomes higher. So p-values that previously weren't rejected are now being rejected, if I understand the comment you're saying, maybe. And so if we are now rejecting more things that we weren't rejecting before, then that suggests that our interval is getting smaller. Anybody else want to try to defend the other direction? I do see two smallers online. I would go with smaller as well. So I would say that if you decrease confidence, you're getting closer and closer to a point estimate. And we know that a point estimate, you have zero confidence that you're right, because it only happened once, and you don't know what it's going to look like the next time around. So any questions about that? This idea that I have now made my confidence interval smaller by scaling it this way. That also tells me that the critical t-value gets larger as the alpha gets larger. Sorry, I said that backwards. The critical t-value gets smaller as the alpha gets larger. And that is what sort of sets up this compression. Okay, great. Questions online about that? All right. So then we moved on to comparison of two systems. And so in this case, we've got one system that might be qualitatively different than another system. You got one arena model and a totally different arena model. You run this for 100 replications, you run this for 90 replications, or maybe 100. And you're going to get a mean performance here, a mean performance there. You're going to get variance performance here, a variance and performance there. And so what do we do with that? We say, well, there's a bunch of different things you could do with that. And it depends on how the experiment is set up. So ultimately, all three things that I'll review here in a second set up the exact same output. which again, whenever possible, if we're estimating the difference in performance between two systems, it is most informative to give us a confidence interval on differences. And so now it's the exact same picture as before, but instead of estimating a single performance parameter, I'm estimating the difference between the two systems. And instead of testing for an absolute performance, I'm testing for 0. So if 0 is in the confidence interval, then I can't tell whether which system is better than the other. If 0 is outside the confidence interval, then I can tell with 95% certainty that one system is better than the other on average. And the half width here is pretty much the same half width formula as in the one sample. We just changed the standard error. So we still use a critical t-value. We're going to need the right degrees of freedom, but now we're taking the standard error on differences as opposed to the standard error on a single absolute, just one sim model. And what formulas we use for the degree of freedom or the standard error depends on how we set the experiment up. We could have done a paired experiment, which has high statistical power, but requires us to really have tight control over the experiment. We have to make sure we run every system 1 alongside every system 2. So every replication is basically replicating in 1 and in 2 with some aspect paired between them. So we're going to run the same customers in both systems for one replication, and then grab another random set of customers, run those random set of customers into both sims, another random set of customer, run both customers into both sims. And that allows us to create differences for every random set of customers that we throw at these things. So both sims have the same number of replications, and the degree of freedom formula is just those number of replications minus 1. And the standard error formula is just the standard error or the standard deviation of the differences divided by square root of the number of replications. So it's the simplest of the three. It gives us high power, but a lot of assumptions and may be very difficult to set up. If we don't have that much control over the experiment, if we have to run our system A separately from our system B, so we don't have any control over the customers. We might have 100 random sets of customers going into system A, another 100 random sets of customers going into system B. We're going to have an estimate of system A's performance that'll be independent of the estimate of system B's performance. And then we have to do a 2-sample confidence interval, which is designed like a 2-sample t-test. Now, if those two systems have the same variance, so there are tests for this. You might have learned some of these tests for this, like the F test. One that I would use is the Levine's test, which tests for what's called homoscedasticity, or heteroscedasticity is rejecting heteroscedasticity. So we're making sure the two systems have the same variance. And so the Levine's test, or the F test, but the Levine's test is a high-powered way to see if two systems have the same variance. If they have the same variance, then I can pool those systems together to get a better estimate of their variance, and I get more power. So I get not as high power as the paired difference, but I get medium power relative to other 2-sample tests. And that gives me this formula for the degree of freedom that'll plug into the T, and this uglier formula for the standard error of the mean, which I plug in here to get my confidence interval. Now, if I run my system A and it's got tight variance, and I run my system B and it's all over the place, and now I'm just trying to compare the means of these two systems to see which one on average is better. In that case, I can't use this one. I have to go to the most generic version, this Welch's version. And in the Welch's version, the degree of freedom is an ugly formula, although the standard error of the mean is not so bad. This has lower power, but fewer assumptions. And so power in this case is going to correspond to what? Like after I calculate my confidence intervals, when I talk about what is a high-powered confidence interval? Does anybody have a guess at that? Remember, high-powered, another way of saying that in your head would be like effectively high numbers of replications. So as you increase the replications, what happens to the confidence interval? That's the same thing that happens as the power. So any guesses? If I was to compare confidence intervals coming out of this group versus this group versus this group. As I decrease power, what happens to the confidence interval? What was that? It gets larger. How many people would say that it gets larger? How many people would say it gets smaller? Why would you say smaller? Uh-huh. Right. So I think the key that you said there is that you're able to reject more. So you kind of have more things that you can reject if it's what do you mean by out of control? Yeah, okay, right. So if the null hypothesis is not true, then you have a greater chance of detecting it. So that is exactly the right sentiment. But the way that plays out is actually as you increase power, the detection of the null, the easier detection of deviations from the null, actually acts like a tighter confidence interval because you end up getting more space between the edge of the confidence interval and the null. So we have to think of the real line as all of the null hypotheses that we are testing. The ones outside of the confidence intervals are the ones we've rejected. The ones inside the confidence intervals, ones we can fail to reject. And so as we're increasing power, this is a reason why power is sometimes called sensitivity. As you increase the number of samples, you're able to detect smaller effect sizes. You're able to detect smaller differences. So if my null and reality are not separated very far away from each other, then a low-powered confidence interval will include both of them because I won't be able to tell the difference. But as I increase power, what's going to happen is my confidence interval is going to collapse around the real value and exclude the null. But if the null is really close to it, the high-powered confidence interval has got to make the confidence interval really tiny to finally put daylight in between the confidence interval and the null. So that's why increasing the power generally tightens the confidence intervals. And we'll see that in a second for a paired difference example here, where we do it without paired differences and with paired differences, and we'll go to giant confidence intervals, and then we'll snap to a paired design, and they'll get really tiny. All right. So give me a couple slides, and if you have questions, let me know. Does anybody else have questions on that? So general rule is higher the power, more sensitive the test, narrower the confidence interval. Questions online? All right. So example, this is from a real paper. So this is an example where it doesn't matter what they're measuring here, but but they report, because it's a two-sampled experiment, the mean difference. So it might be hard to read, but they say we have data sets which are named Lilith and Hermione. It doesn't matter what they're named, but they say that in both of these data sets, they mention that these data sets compare a treatment A versus a treatment B in both of these data sets. And they say in Lilith data set, they give the mean difference is minus 0.071. That point estimate doesn't really matter that much. And then they say the 95% confidence interval goes from minus 0.2 to 0.061. So it includes 0. And then they also listen for Hermione. They give a mean difference. They say mean difference right there. They give the confidence interval on that mean difference from minus 0.266 to 0.09, also includes 0. So both of these confidence intervals correspond to a t-test p-value that is greater than 0.05. But then, in fact, they don't even, I think, list the p-values in here. They just mention paired t-test and then give the confidence interval. Now, but down here, they say for these other data sets, they say that the mean difference for this other data set is minus 0.223. That's a point estimate, doesn't really matter. And then they say the 95% confidence interval is from minus 0.4 to minus 0.04. And so that basically is a confidence interval that is bounded away from 0. And so that is a significant difference. So the p-value is going to be less than 0.05. So they say here, one-tailed, in this case, these one-tailed tests, it's always dangerous to use a one-tailed test, but in this particular case, it made sense for them. And so, and then they even give a p-value of 0.01. So this specifically, they say that it's a significant difference. And they just list the confidence interval, and it doesn't include 0, and that's how they do it. So that's how you do it in data science or in science in general. If you're comparing two groups, you can just say, I did a Welch's t-test and the p-value is this, but it's going to be far more informative if you actually list the confidence interval, because it will give someone an estimate of the magnitude of the difference between the two groups. And if that difference doesn't include 0, that means it's a significant difference. So that's our 2 sample example. Any questions about that? Okay, great. So another common way to visualize these things, in especially paired cases, is to plot the pairings out. And you will see this again in today's lecture, because I'll revisit what we did in the muffin baking sim at the very beginning of the semester. But again, doesn't matter what these data are, but this is from actually a colleague here at ASU, and a friend who had a paper in 2001 where he had these, again, so I work with a lot of social insect people, and so this is an ant example. And so these are, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 colonies that he's lettered A through J. And in each one of these colonies, they've studied their response, and it doesn't matter what this response is, but basically under 2 treatments. And he said, so I'm going to say one colony, I'm going to put them in a one-walled nest, and another colony, I'm going to put them in a 2-walled nest. I'm sorry, in that same colony, I'll also put in a 2-walled nest. So he studies their response in these things, and I'm going to do it across 10 colonies. So each colony has seen both treatments. And so it wouldn't make sense to compare colony A's response to one wall to colony H's response to 2 walls. But it does make sense to compare colony A to itself. So by plotting it this way, we can see the variance across the colonies, but we can also kind of forget that the variance across the colonies exists. So we subtract away the variance, and all we really care about are the differences between one treatment shown in circles and the other treatment shown in X's. And we can show that for 9 of the 10 colonies, the X is greater than the O. And so that is going to tell us that that most likely, if you do the t-test, as he does here in the caption, that this one-walled treatment is significantly less than the 2-walled treatment. And this is using a paired example. So if you have a small number of replicates in a paired design, sometimes you just plot all of your replicates and you kind of plot them like this. And down here, just to confirm, he said paired t-tests, one-tailed, again, doesn't matter about the one-tailed, gives the t-value, says p is less than 0.05. And so did a paired t-test, which is basically a one sample t-test on these differences. And that's basically saying that the mean difference here is bounded away from 0. And so yeah, that's how we plot that. So any questions about this plot? And again, we'll revisit our muffin baking sim, where we'll basically have each one of you was given a different set of customers. So I could just say that, like, well, this is, student 1's set of customers, student 2's set of customers, and the X's could be viewed as the greedy policy for the oven, and the O's could be viewed as the always, or the nearly full policy for the oven. And then we could compare how greedy versus nearly full do for each student, and then compare the differences across each student. And that's a paired design. All right. Questions online? Great. Now, if you can't do a paired design, typically the way we summarize these things graphically is just by plotting the confidence intervals, plotting the standard errors, or just plotting the data in some summary format like box plots, like box and whisker plots. And so in this case, this is from, looks like a genomics. or epigenomics study here, where they were studying people of less than 45 years of age and greater than 45 years of age, and how much methylation they've seen throughout their DNA. And this is in percentages. And so they're trying to say, is there a difference in methylation for those who are young versus older? And so they just plot, well, here's the methylation data summarized as a box and whiskers plot. Here's a methylation data plotted in box and whiskers plot. And just by looking at it, it looks like the older have more methylation, but we don't know for sure. We run a two-sampled t-test or something similar, a two-sampled test on these data. And then a lot of times we just connect the groups we're comparing and put their p-value there. And that says p is 0.001, which is less than 0.05. So that implies that yes, to this statistical significance, then when you're older, you do have more methylation. So that's the way we summarize it when they're not paired. All right, any questions about that? Pretty clear. So if you have a small number of space, just give me the confidence interval and tell me what type of confidence interval it is, paired, pooled, or Welch's. If you have enough space for a figure, consider plotting something like this for paired and something like this for unpaired. All right. No questions on the 2 before we go to the 3 or more? All right, so then 3 simulations here. So we have an as-is system, a one proposed change, another proposed change. So now I can doing 3 or more. And so with this, we fall into the statistical area of ranking and selection, or RNS, where we like to compare all models to each other, or at least pick the best. So we either want to rank them or at least select the best. So we can do ranking by doing a whole lot of pairwise comparisons, but we would like to minimize the comparisons if possible. And so if you can manage to choose like a benchmark system, we're going to compare them all to the benchmark and see who's better than the benchmark. Well, that's a lot less comparisons than comparing them all to each other. So if we just need to find one system at least that's better than a benchmark, then do that. But if you really need to rank all of the systems, that's a whole lot of pairwise comparisons, and it makes it a lot harder to do, because what you're going to need to do to be statistically rigorous is count up all of those comparisons, and on every pairwise comparison, you'll have to divide that alpha for each pairwise comparison by this number of comparisons in order to be rigorous, in order for the family-wise error rate to be alpha itself. So if you want to make sure you've selected a best within some epsilon with a 0.05% error rate, then you're going to have an error rate for each pairwise comparison that's way, way lower. And that is going to hurt your power. So you try to minimize comparisons whenever possible if you have to resort to doing a bunch of pairwise comparisons. Now, an alternative is you can go and use an ANOVA, an analysis of variance. And so an ANOVA, which hopefully you remember from like 380, allows you in one shot to say, I got 5 systems across the bottom here. I'm measuring them all with respect to one response variable. And the ANOVA will have a p-value. P is less than 0.05. What that'll mean is one of your systems at least is different than one of your other systems. That's all the ANOVA means. It doesn't tell you which one's better than which. So then any good statistical tool that has the ability to give you an ANOVA will then ask you how you want to do a post hoc test. And a post hoc test like the Tukey HSD test or Fisher's LSD, this will be a selection option, and that will actually rank them. And they'll usually give little letters above them like, all right, these 2 are in group A, these 2 are in group B, these 2 are in both A and B. And the grouping tells you which ones you can't tell apart. So anybody in group A, you can't tell apart from each other, statistically speaking. Even though they look like this one's greater than this one, we actually, statistically speaking, within the error parameters we've given, we can't tell them apart. B, we can't tell these Bs from these Bs, just can't tell them apart. But we can tell that both of these Bs are statistically different to a significant level from this group down here. We can't tell which one this one goes into. It sort of belongs to both groups. So if I'm wanting to choose the system with the minimal amount of this parameter, I choose one of these in the A group. And if I'm trying to choose them with the maximal, I choose one of these in the B group. So that's the way I might read this, but I can't choose between the B's or between the A's. Yeah. Mm-hmm. Yeah, that's right. So if we were thinking this in terms of pairwise comparisons, then if I were to do the pairwise comparison between, let's say, this one and this one, it would be less, P would be less than 0.05. It would reject that they're similar. If I were to do the pairwise comparison between this one and this one, P would be greater than 0.05. I can't tell a difference. Now, if I were to pick any one of these B's and do a pairwise comparison with this middle one, P would be greater than 0.05. If I were to do any one of these A's and do the pairwise comparison with this one, P would also be greater than 0.05. So I can get P less than 0.05 for this group versus this group, but I can't get P less than 0.05 for this with either one of these groups. Does that make sense? Yeah, great. So any questions about that? Great. Now, the downside of doing this is I've told you several times that like we often like to run a couple of sims, do a pilot study, maybe run some more sims, do another, and grow the number of sims we have. To do an ANOVA with a Tukey test or a post hoc test, we kind of need to know how many we're going to run all our replications first and then do the test. There's no like sequential sampling. You can't like do the test and then rerun and then do the test again and then rerun. Then you get into something called p hacking. So it's not good statistical procedure. So there are ways to do what we refer to as sequential sampling, where you run a couple of things, you generate some data, and it tells you how many more to run. And in the last lecture, I had to skip over it, but the book goes over in detail one of these methods that you could do that. But fortunately, there are those types of tools are sometimes built in to these sim tools. So if you have to do it yourself, there are references. So you can look at the ranking and selection section of the book. I'm not going to quiz you on all of the steps between that, but just know that in the book, there is a process that talks about, well, how many initial replications to run, what stats to do in between, and how those stats will tell you in an honest way how many more replications to run, so that the best one will be the best with a 0.05% or 0.05 error rate. And so those processes exist, and that's what we refer to as sequential sampling. So taking some samples and then making decisions about how many more samples to take. Now, this select the best stuff, fortunately, a lot of these statistical tools, even Arena, have them built into it. So if you're doing your final project, or even homework J2, you can go into the process analyzer and you can give it 3 scenarios. Scenario 1 might be this number of baristas. Scenario 2 is another number of baristas, and scenario 3 is another number of cashiers. And so you can say, load up this model or these multiple models, configure them with these different things. So you have to set like the number of baristas as a global variable, and then this will have access to it, and it can change all those global variables. So it can reconfigure your sim for you. And then you can tell it to say, I want you to run 5 replications for scenario 1, 10 for 2, 13 for 5, or just them all for 10 or something like that. It will run all of those. And then you can say, summarize all of your outputs as a box and whisker plot. And when you ask it to do that box and whisker plot, you can tell it to select the best. And it'll say, what do you mean by best? Is best low or high? And then it effectively does an analysis of variance with a post hoc test, but its post hoc test isn't trying to rank all of them. It's just trying to highlight which one's the best, where best is determined by you, min or max. And so in this case, I ran this example and I selected best to be the lowest. And it found that scenario 1 was much higher than both scenarios 2 and 3. It could not tell a difference between 2 and 3. So for me as an operations researcher, I would say, that it's not going to be much harm for me to select 2 or 3. I can select them arbitrarily. I could choose the one that's cheaper. And there's because there's not really any noticeable difference between them, but I should not select scenario 1. And that's all done for me inside the process analyzer. I just need to tell it which ones to compare, and it just spits that out for me automatically. And then I also, if I want to get crazy, could go into the OptQuest, which is another tool that's introduced in Lab 10. And in OptQuest, I don't even tell it what replications to run. I can say, here's a model. I have to get a single model, not multiple models. That's nice about Process Analyzer. I can give it multiple models. But in OptQuest, I say, here is a model. And here's a number of global variables representing my decision space, representing things that I want to change. And so I can say, in this case, because it's kind of modeled after Lab 10, I think, I have a global variable called max batch, another global variable called restart, and I have a constraint where I want to make sure that this objective value that I've identified, so maximum wait time or whatever, never goes above or below a particular amount. And then otherwise, I want to minimize some other objective. So I can say, go and just walk through all of the possible decision variables. And for each one of them, run as many replications as you need to be able to differentiate it from the other decision variable choices, and then gradually rank them all so that we can select the best. And it will walk through, and notice there's a simulation down here. You can watch it running, and it'll say the first simulation it ran, it got this value, but it's red because it was outside my feasible space. The next one, it went in the wrong direction, so then it tried another value to go back in the other direction. And eventually we'll call it generation 18, it found one that was lower, and I wanted to minimize whatever this is, wait time or something like that. And so this will automatically do that optimization for you without you having to make any replication parameters. So it's a pretty cool tool. And you'll find OptQuest in other tools. This is not made by Rockwell Automation. It's licensed by Rockwell Automation to use with Arena. If you use AnyLogic, which is another tool that competes with Arena, they also license OptQuest. So if you know how to use OptQuest in Arena, you know how to use it in a lot of other tools as well. All right, so any questions about that? How to use, or the basic idea behind the process analyzer in OptQuest? Yeah. Mm-hmm. Right. Mm-hmm. You're asking why is comparing to a benchmark a compromise over ranking? Is that? Oh, well, yeah. So the question there is, so why is comparing to a benchmark in some ways better than going through the whole process of ranking everybody? Is that the sort of question? That's Oh, right. Yeah. So if I do a benchmark, like let's say my benchmark is my as is system, and I have 4 other alternatives I've come up with. I have no idea if they're better than my as is system, and I have no idea how they compare to each other. If I just need to find one solution that's better than my as is system, I use my as is as a benchmark, and then I compare each one of the 4 to my benchmark, 4 comparisons. But I don't compare them to each other. So because I didn't compare them to each other, I didn't actually do a 2-sample t-test across, with each one of them, then I'm not actually going to rank them all. So it might be that I pick a system that's better than my benchmark, but so like if this is throughput, so my benchmark throughput is down here, and all 4 of them have some throughput that's up here. Since I formally didn't do a 2-sample t-test across these 4, I don't know how they compare to each other. I just know maybe that 3 of the 4 are better than my benchmark, and maybe 1 of them is worse than my benchmark. Well, I know I don't choose the 1, but I can choose any of these 3. Now, I might not have chose the best of those 3. Well, in that case, I might need to do a ranking and selection of all 5 systems, benchmark in those 4. And if I do that ranking and selection, that's going to require a lot more pairwise comparisons. It'll be whatever, 5 choose 2 or something like that. Because, each one of them has to be compared to each one of the other ones. And that is, each one of my pairwise comparisons is going to have a really low alpha because it's going to have to be corrected for this huge number of comparisons. And that's going to mean basically my confidence intervals on each one of my pairwise comparisons are going to be large. So if I do the ranking and selection problem, I might be trying to rank them all, but in the end, I might actually not be able to tell the difference between any of them because each one of the pairwise comparisons, their confidence interval is going to be so large that they're all will contain 0. So the more comparisons you do to avoid the fishing problem, the more conservative your test gets, and you end up maybe being less able to detect fine scale differences in the problem. So whenever possible, you want to use as few comparisons as possible, or if you can, just do a proper ANOVA with a post hoc test. And in that case, the ranking and selection is sort of for free, but you can only do that if you're not like in simulation. You very often, your simulations take so long, you don't want to run 100 replications. You want to run 5 and then see if you need to run another 5. But yeah. You could, I mean, so what you don't want you never want to take the same data and keep running stats tests on it because then it's fishing. But what you could do is you could say, I ran my previous experiment and it said of these 4, these 3 were better than my benchmark. I'm now going to run a new experiment where I only consider these 3. And then I'll gather more data on those 3 and then maybe be ranking on those. So the first experiment was a screening experiment to help you set up the design for the second experiment. Okay. So any other questions about that? Great questions. These are a lot of sort of design of experiments questions, DOE questions. We have courses in DOE that those of you interested in like 4+1, definitely, if you're interested in these sorts of questions, take DOE, design of experiments, which I forget the number. Does anybody know? 572. Then you'll go into these sorts of details in far more detail than you get here, where I'm just kind of surveying the basic idea. Okay, great, excellent. Questions online that I missed? All right, so new section, VRT, variance reduction techniques. This is definitely a design of experiments type of thing. We've now learned how to build sims, how to compare sims. Now we need to figure out how to optimize the operation of our sims so they're faster, so we can gain the most insight for the fewest computational budget. And we've already gotten a little bit of a sense of this. But the basic idea is that if I'm estimating a performance parameter, there's its mean from across the replications, there's a standard error of the mean. We've talked about how if you run more replications, the standard error gets tighter. The confidence interval gets tighter. And so fine, if I want to increase the sensitivity of my analysis, then increase the number of replications, great. Well, that's costly. So what else could I do? Is there a way I could redesign my experiment so that the fundamental variance in my system is less? And that's what a variance reduction technique is. And so we're going to try to control for other sources of variance. So there is a natural source of variance, system A, system B, that's a source of variance. But we want to try to control for other sources of variance that are just noise that require us to run more replications. If we can somehow control for them, and control is just a fancy name for accounting for sources or even removing other sources of variance. We control for them. So the only variance left over is the tiny little bear variance that actually has to do with our 2 system types. So across this lecture and the next one, and possibly if we need it, we'll bleed over into the kind of wrap-up lecture on Tuesday before Thanksgiving. We're going to go over these kind of 4 basic variance reduction techniques. Coordinated random or common random numbers, control variates, anesthetic variates, and importance sampling. And so today we're only focusing on CRNs and control variates, and we've seen CRNs before. So control our common random numbers, CRNs here, is also known as correlated sampling, matched streams, or matched pairs. You've done this in homework G3, and we did it actually, whether we realized it or not, in one of the first labs on the muffin sim. And so the idea here is to block your simulation experiment so your two sims effectively take the same inputs. And so I've got two sims, they run the same number of replications, I provide the same input to both pairs of runs, to both systems. The normal way to do this is to set the random number seed the same for every replication. So if I've got two sims of a coffee shop, replication one is going to use replication one for both is going to use random number seed 462. Replication number 2 is going to use 1,462. Replication 3 is going to use 2,462, and so on. So the pairs of replications use the same random number seed, and that helps guarantee that the customers that are drawn are going to be effectively the same customers going into both sims. And then we can look at their outputs and pair their outputs up and then compare their differences. Why this hopefully will work is this variance formula. The variance in the difference of two variables is equal to the variance in one plus the variance in another minus a scale version of their covariance. And this is another form of the covariance formula down here, which has got the correlation coefficient times the individual standard deviations. So what this is saying is that if across my replication, there is covariance between my two different sims, then it will reduce the total amount of variance. So if I were to do a two sample t-test without this design, then the variance I have to deal with would just be these two together, just the sum of the variance in one plus the other. But if I can pair them up so that a hard set of customers for one causes the delay to go up, and then an easy set for the next replication causes them both to go down. If they're both kind of moving around the same way, they both treat the inputs the same way, there's correlation across replications, and that will end up reducing the variance in this difference. And that will reduce the size of our two sample confidence interval. That's what goes on here. But we have to then use the paired difference t-test, or effectively the two sample confidence interval that corresponds to the paired difference t-test. So we saw this in the muffin baking oven simulation. This is lab 2. And so where you were the computer simulations, and I said everybody with an ASU ID that ends in 0 gets these customers. Everybody with an ASU ID that ends in 1 gets these customers. You can think of the end of your ASU ID as the random number seed. And so I gave you 10 random number seeds. And so each one of you went off and simulated the greedy sim and the nearly full sim. But then across, so from one person to another, you might have had a different random number seed and thus had different customers to put in there. So I can pair these together so that this group is not independent of this group. So we can think of this as one student's. So this line represents one student who this is their greedy output and this is their nearly full output. This line here represents another student where this is their greedy output and this is their nearly full output. And now we're not looking at the individual points, we're looking at the slopes of those lines. And all of those slopes, even though the points are all over the place, the slopes are all going in the same direction. They're all positive. So we can take the differences of those, and I already showed you something that looks just like this. This is the typical way to plot, if you have a small number of replications, a paired, paired data. And so we've got the batch schedule. These are the end of your ASU IDs in that lab, end in 0, end in 9. So those that end in 0, this was your output for greedy. This was your output for nearly full. Those are into 9. This was your output for greedy. This is your output for nearly full. And I can focus just on the differences. I actually don't care about the absolute position here. I just care about the length of these dashed lines. Now, if I plot the length of those dashed lines, these are all of the lengths. And those lengths because of what I decided to find as top versus bottom, are all negative. They're all bounded away from zero. So I end up getting a significant difference here. So if I were to generate a confidence interval, which I didn't, but maybe I should have, then that confidence interval will be completely bounded away from zero. So it would be sort of down here somewhere. And that would tell me that these two systems are different. And so that's the example I'm hoping you're seeing here, is that there is variance across the random number seeds, but that variance is subtracted out. So it is true that whatever customers corresponded to this random number seed seemed to be much harder than other customers, or this one up here. Whatever customers corresponded to this random number seed were much harder than the customers that corresponded to this random number seed, but they were harder for both. So if I go from seed 5 to seed 8, the red dots go up and the blue circles go up. So they both went up. And so that is what I mean by them being correlated. So we can now subtract off the variance that is due to the difference in inputs, so that the only variance that's remaining is the variance that's actually due to the system. That's what pairing things up to. And that's what we refer to as common random numbers. And the book's got an example of this too. So in the book, when you go to their CRN section for this chapter, they've got a simulation of an MM1, so a single node of a single server, single one queue system. And it's got, like I said, one server, and then it's got another compared to 2 servers. And we'd expect that when you add another server, that, I forget what they're plotting here, let's say its waiting time would go down. And so they've plotted the one server case as solid dots, the 2 server cases as circles, but they're not paired. They're kind of artificially grouped together. And you can see that the circles and the dots are all over the place. Now, when I pair them up so that I put the same inputs into both systems, then notice that all the differences are super small. So the variance that I'm seeing here, like this one here, this long line, that wasn't a fundamental difference between the system. It was just that this set of customers was much easier than this set of customers. And those kind of an unlucky pairing. But when I pair the same customers together, then now I can detect very small differences between these systems. And if I look, the solid dot is pretty much always above the open filled dot. So the waiting time for these customers is always less with 2 servers, just not quite as less as you might expect. So we detected a small difference, and we could subtract off this huge amount of variance that was actually in the customers. That's common random numbers. So before I show you how to do that in Arena, are there any questions about this general idea? And we'll probably end up doing antithetic variance next time, which is fine. Okay, questions online? And I hope you can see that if you did the, if you did a confidence interval of these differences, it would be much bigger than a confidence interval of these differences. All right, so how do you do this in Arena? You have to bring up the elements panel, which you might have to, I think that might still be in the old, I think it's still available, but it's not up there by default. So you may have to add it. But when you bring up the elements panel, then you have to drag in the seeds block, and then you go into seeds, and it'll have if you drill down into it, it will have an empty list of seeds, but you can add one. And we've seen this before when we were talking about random number generation, and you can give a name to your seed, well, what we'll call it a stream. So you can give it an identifier, a stream identifier. You can type anything in there. If you put the number 10, then it will default. It'll say this is the default random number stream. It's going to have these properties. You can leave the seed value blank, but under the initialize option, you can drill down into that and change it to common. And what that does is, and this is just summarizing everything I just said here, is it ensures that every replication starts with a random number seed 100,000 apart from the previous seed. So it might start with 62, and then it'll be 100,062, and then 200,062. And by doing that, even if you run different models, you'll be sure that they always start with the same random number seed. So you can pull that into the output analyzer and it'll do a paired test. So how do you make use of that? If you name your own, you can go into any one of these blocks that takes a random number expression, and the second argument of the, or the last argument of the expression is optional, and you can put in your stream. If you've changed the stream, the number 10 stream, then you don't have to do this. But if you added your own named stream that's initialized with common random numbers, then you can say, instead of expo2, you could do expo2 comma, and then the name of that stream. And it'll be sure to draw from the stream that is locked in step with the replication, so that it always starts with a known common or a known random number seed. And so this is just summarizing that here. So you can go into a create module or a process module or whatever, and wherever you would previously do just expo5, you can add a final argument that is the stream that you've initialized with common. And if you've initialized 10 with common, you don't have to do this because it automatically does it for the default random number stream. Then after you do that, you can then go into the output analyzer, and it has a paired difference t-test. You can say, here's data, here's 20 replications of data I took from one simulation. And then you can say, here's 20 replications I take from another simulation. And you can bring them up in the output analyzer's t-test. And then you can check a box to say that you want the data to be paired by replication. And it will know to use a paired difference t-test instead of a two-sample t-test. All right. Only the last slide I have on CRNs here, I think, doesn't always work. So it's another one of those cases where you should probably pilot, with a few number of replications, study the variance across one replication, study the variance across, one system with those few replications, the other system with those few replications, and then study the difference, the variance of the difference between those two. And if the variance of the differences is less than the sum of the variance across the systems, then that means that CRN is probably going to work. All right, so any questions about CRN? Like I said, I'll hold antithetic variance for next time, and that's totally fine with our schedule. Yeah. Mm-hmm. That's right. So that, yeah, if you open up system one in Arena and you go to replication setup and you set up for 10 replications, and you've got this common thing set up, then of those 10 replications, it will be like, it'll be whatever the standard random number seed is for replication one, then it'll add 100,000, add 100,000, add 100,000. And then that way it adds 100,000 to where it started. So it's not where the random number seed ended. And then if you go into your other model, go into replication setup, set it for the same number of replications, and then you go in and set it up for common, and every replication will be seeded the same way in both, even though you opened and closed Arena between running. All right. Well, I don't want to hold you too long, but I'm definitely happy to take any questions after if there are any. But so the question here, the attendance question, just putting the link in the chat, is yeah, I'll do the high-powered one again. So generally speaking, a higher powered two-sample t-test will have a smaller or larger confidence interval than a lower powered two-sample t-test. So if you increase the power of a test, do you increase or decrease the size of its confidence interval? And that's all I've got for you. So we will see you on Thursday. Unless you've got other questions, happy to take those after.